Hello, everyone. So now we will talk about the case where, again, we will infer information for the difference of two means, but, well, we don't know sigma. So remember, um, sigma unknown. So remember the case where we talk about mu. So for mu, if sigma is known, okay, if we have sigma, then we just use z and say that x bar minus mu divided by sigma divided by root, and that's c. If sigma is not known, then we just use t random variable, x bar minus mu divided by now s divided by root 10, okay? So in fact, here we would exactly have the same thing, the same way of thinking. But here there's a little bit difference. Well, um, we just divide this case into two. We say that, okay, we don't know variances, but can we say that they are equal to each other? If they are not known, but they are equal to each other, well, that's a bit powerful assumption. But if you can say this, then your results are more, let's say, powerful. If you cannot say this, then if sigma 1 is not equal to sigma 2, then you will have a different formula and different way of calculating the confidence intervals and hypothesis testing. In both of them, we will use t-distribution, but there's a little difference, okay? We will see them. So let's assume the first case, sigma 1 square is not equal to sigma 2 square, okay? So we don't have any information about the sigmas, okay? And we cannot say that they are equal to each other. Or, in fact, later we will see to make a hypothesis test regarding this, whether sigma 1 square is equal to sigma 2 square or not, okay? So if you just make this test, and if you cannot reject the hypothesis that sigma 1 square is equal to sigma 2 square, then you can use the case where both variances are equal. But if you reject the hypothesis and it turns out this is true, then you have to use this case, okay? So, okay. Well, x1 bar and x2 bar, let's assume they're just from samples of N1 and N2, and they are approximate normal populations, okay? Approximate normal populations with unknown and unequal variances sigma 1 square and sigma 2 square, okay? And also let S1 square and S2 square be their sample variances to estimate their population variances sigma 1 square and sigma 2 square, okay? So okay, just go back and let's try to remember what we have. We said that x1 bar minus x2 bar minus mu1 minus mu2, okay, divided by sigma 1 squared divided by n1, sigma 2 squared divided by n2. So this was the case for the previous, let's say, hypothesis testing. Now we said that we don't know sigmas, right? We don't know sigmas. So, okay, let's see what we can do. So we said that this is standard normally distributed. Since I don't know sigma 1 and sigma 2, but I have S1 and S2, what I can do is just erase this, okay? And write S1 square here and erase this and write S2 square here, okay? Now what happens, I have x1 bar minus x2 bar minus the mean and divided by the sample standard deviation. So this is, just recall, this is an analogy. This is an analogy to, let me just take the eraser here. This is an analogy to remember, x bar minus mu divided by s divided by root n. So this was t-distributed with n minus 1 degrees of freedom. And in fact, we will see that, well, this is also t-distributed. How many degrees of freedom? We will see it, okay? Now, okay, so this is my test statistic, okay? So I will just use this test statistic in hypothesis testing and then for constructing confidence intervals. So remember, this is in fact my step one, okay? Step one, mu1 minus mu2 is equal to some difference d0. It can be 0 or it can be any other value, versus mu1 minus mu2 is not equal to d0. Okay, so what is step 2? Step 2, just find your test statistic. My test statistic is this thing. Okay, so this is my test statistic, which is a t random variable. Okay, t random variable. Okay, then what is step 3? Okay, let me just write it here. Step 3, find what? Find the critical region, which is, so since we are using t, that's very easy. Minus t alpha over 2, t alpha over 2. Okay, this is my critical region. What is step 4? Step 4 is calculate your T observed. Okay, what is T observed? That's extremely simple. What you do is you just use this formula. Okay, this formula, plug in the values that you have see there to calculate the T observed. How? This is equal to x1 bar observed minus x2 bar observed, okay, minus mu1 minus mu2. Mu1 minus mu2 just comes from the hypothesis, which is d0 divided by s1 square. In fact, this is the s1 that you calculated from the sample, s1 square, and this is s2 squared divided by n2, okay, in square root. So this is your T observed, okay? And step 5, what you do is just conclude, okay? Conclude. How? Well, if your T observed, if this is in the critical region, then you just reject the hypothesis. If it is not in the critical region, then you don't reject this, okay? Great. Okay, how about the confidence interval? Well, remember the confidence interval, how do we find the confidence interval? So I have something like this. So probability that minus t alpha over 2 smaller than t, this is t alpha over 2. So instead of t, what you will do is you will just plug in this value, x1 bar minus x2 bar minus mu1 minus mu2, okay, divided by s1 squared and 1, s2 squared and 1, and 2, sorry. After some algebra, you will see that the confidence interval is equal to this thing, okay? So the difference between the unknown mu's is 1 minus alpha times 100%. You are confident that the difference between mu1 and mu2 is between this and this, okay? So as you might see, this is very similar to, okay. So before getting into this one, so what is the degrees of freedom? Well, that's a bit mess, okay? That's a bit weird formula, but this is what we have in terms of degrees of freedom, okay? So this is s1 squared divided by n1, s2 squared divided by n2, and just take the square of this. Then s1 squared over n1 squared over n1 minus 1 and blah, blah. This is the degrees of freedom, okay? So this is a bit what? This is a bit messy formula, okay? But okay, you don't have to memorize this. What you will do is, if you're asking the question, just put in the values and try to calculate this degrees of freedom. And if you just compare it with the previous case where you know sigmas, okay, where you know sigmas, just look at this one. So this is the confidence interval. This is the confidence interval where you know sigmas, okay? So confidence interval when sigmas are known. See this, they are very similar to each other, okay? Just look at this one. Okay, just look at here. So the only difference is that, well, you don't know sigmas, hence you just plug in s1 squared and s2 squared. And since you cannot use sigma, instead of z alpha over 2, I'm just using t alpha over 2. Okay, they are very similar to each other. Now the next step is, sorry, the next step is, so what we do is, until now we cover sigma 1 and sigma 2 are known, okay, are known. Then we just cover sigma 1 is not equal, sorry, sigma 1, sigma 2 are not known, okay, let's say unknown, unknown, but sigma 1 is not equal to sigma 2. Now this is case 1, this is case 2a, okay, and this is case 2b. Sigma 1 and sigma 2 are unknown, but I can assume that they are equal to each other, okay? Just look at this one, equal to each other. Now, okay, so before getting into this, remember in the previous slide, we said that, well, this is a t random variable. X1 bar minus x2 bar minus what? Minus mu1 minus mu2, which is d0 from the, so if you are just making the hypothesis, it is just d0 from the null hypothesis. If you're just making the confidence interval, then you just write it like this, divided by what? Divided by S1 squared divided by N1, right? S2 squared divided by N2. Now, the assumption says that, well, sigma 1 squared is equal to sigma 2 squared. What does this mean? So you have sigma 1 squared equal to sigma 2 squared, which is equal to a unique sigma square. Okay, you don't have two sigmas. You only have one sigma. What does this mean? So I have S1 squared, which estimates sigma 1. I have sigma 2 squared, which estimates sigma 2 squared. I don't need two estimates because I only have one sigma. I will just use a single estimate for the single variance, which I will call as the pooled estimate. Okay, so this is the pooled estimate of two populations. So let me just put that value here. So this is equal to x1 bar minus x2 bar minus mu1 minus mu2. Okay, divided by, so instead of s1 square, I just put sp squared divided by 1. This is sp squared divided by n2. Okay, so what is next? This is equal to, so this part, okay, I can just write this part as, this is equal to sp squared 1 over n1 plus 1 over n2, okay, in square root. And you can just take this out. So this is sp times 1 over n1 plus 1 over n2, right? So if you assume that, well, the sigmas are equal to each other, then this is what you have, right? That's great. So you can just use now, instead of this one, you can just use this t random variable, right? This is x1 bar minus x2 bar minus mu1 minus mu2 divided by sp times in square root 1 over n1 plus 1 over n2. Okay, so this is my new t random variable. I will just use this t random variable in hypothesis testing and in confidence interval. And the difference between this one and the other, the previous tier random variable, is that, well, the degrees of freedom here is very easy, okay? N1 plus N2 minus 2, okay? So the degrees of freedom here is very easy, okay? This one is easier, great. Okay, so you know what's written here. In fact, this is the same thing that we have written so far, okay? So this was for the hypothesis testing. You just use this t, so this part. Let me just erase this. Let me just erase this part. Okay, that's better. So, okay, so this is the t random variable that you will use in hypothesis testing, and of course for a confidence interval. So the whole procedure is the same. How? Step one, you just write the hypothesis, okay? So this is my step one, this is my step one. And step two is just find the test statistic, which is this is step two. And step three, your critical region, okay? The critical region is here, okay? This is the critical region, this is step three. Step four, just calculate your T observed. This is step four, right? Step four. And this is what, this is conclude, okay? Step five, conclude, step five. Okay. And this is, okay, this is the confidence interval. right? So just look at the confidence intervals. So mu1 minus mu2 is between, again, x1 bar minus x2 bar minus t alpha over 2 times sp times 1 over n1 plus 1 over n2. Remember the previous one, mu1 minus mu2, I will just write the right part, x1 bar minus x2 bar plus t alpha over 2 times, remember the previous one, it was s1 squared divided by n1 and s2 squared divided by n2. Okay, so see, it's very similar, but in this case, okay, in this case, what I do is, since I have a single s, I just write sp squared and sp squared and just then take this out. Okay, so this is my confidence interval. Well, as I said, the degrees of freedom is n1 plus n2 minus 2. So, okay, so this is a good one, easy one. And how to calculate the pooled estimate for the variance, okay? Because in general, in the questions, we are just given s1 squared and s2 squared. So what you can do is you can just multiply s1 and s2 by their by just corresponding um, sample sizes and divide by the total sample size minus 2. Okay, so this is how you calculate the pooled estimate for the sigma. Okay, when you are just given sigma 1 square, sorry, s1 square and s2 square.